You might think the battery pack is the most critical part of an EV, but looking through this stack of engineering white papers we have today, it's clear the real power player is, well, completely hidden.
Yeah, it's totally behind the scenes.
Right, like a tiny silicon carbide chip is actually what dictates whether you get 300 miles of range or just get left stranded. So today, we are doing a deep dive into the highly technical architecture of EVs, specifically the inverter, the DC-DC converter, and the battery management system.
And, I mean, we are navigating some pretty dense engineering today.
We really are. But mapping out how these components interact is key to understanding what separates an average EV from a truly great one for you. And we're going to cut through all that jargon.
Absolutely. I mean, looking at the teardown reports, you can see how the whole industry is just obsessing over the inverter right now. Its main job is taking DC power from the battery and converting it to AC for the motor.
Right.
But the big architectural shift we're seeing is the material itself. They're moving from traditional silicon to silicon carbide or, CC chips.
Because traditional silicon chips suffer from those microscopic swishing losses, right? It's kind of like trying to run a high-pressure water system, but with a leaky hose. You're just losing precious energy as heat every single time a valve opens and closes.
That is a perfect way to put it, yeah.
So CISA essentially patches those leaks. Because it can handle much higher voltages and switch states a lot faster, that efficiency reduces heat loss by up to 70%.
Which is huge.
It really is, and it translates directly to like a 5 to 10% boost in your driving range.
Exactly. And that heat reduction is crucial when you are pushing massive power.
Mm.
But, so here is the architectural challenge, right? You have this 800-volt battery pack to spin the motor.
Right, massive voltage.
Yeah, but if you send 800 volts straight to the navigation screen, or like the power window.
Oh, they'd instantly fry.
Instantly.
Yeah.
Just poof. So you need the DC-DC converter to step that massive voltage down to a safe 12 volts for all the accessories.
Right, but looking at the specs for these elite EVs, a basic step down just isn't enough anymore. Like, the gold standard now is a converter that's bidirectional and liquid cooled.
Yeah, it's definitely not a one-way street anymore.
Right, it actually uses the 12-volt battery to wake up the high voltage systems before you even start driving, all while dumping any excess heat right into the cooling loop.
Exactly, and coordinating that entire high-voltage handshake requires some serious processing power. That's where the battery management system, the BMS, comes in. It's basically the brain of the whole operation.
The brain, right.
Yeah, and the newest teardowns show these systems running, like advanced mathematical models and AI. They can actually predict thermal runaway, a battery fire, hours before the chemistry actually destabilizes.
Oh, wow. And the cell balancing mechanisms in these BMS units are what really caught my eye in the sources.
Oh, yeah, the active balancing.
Yes, because instead of passive balancing, which is basically just bleeding off excess voltage from the fullest cells as wasted heat just to match the lower ones, the premium models use active balancing.
Which is so much smarter.
It is. It's essentially high-speed energy arbitrage. The BMS uses these tiny capacitors to constantly shuttle voltage from the strongest cells directly over to the weakest ones. It levels the pack without wasting a single watt.
Right, that's perfectly efficient.
But wait, if active balancing is that much more efficient, why isn't every single automaker doing it? I mean, is it just a hardware cost issue?
Yeah, it's primarily cost and complexity, to be honest.
Yeah.
Adding those capacitors and all the control logic to shuttle power on a cell-by-cell basis is just expensive. Automakers are always balancing range against manufacturing margins,
Makes sense.
though they are finding efficiencies elsewhere, like with WBMS, which are wireless systems.
Wait, wireless battery management?
Yeah. By communicating via radio frequency, they can strip out all that heavy physical wiring. It cuts weight and frees up physical space for more active battery material.
That is incredible. Okay, so taking all this theory into the real world for you listening, where do you actually find this holy trinity of EV tech? The 800-volt architecture, CP inverters, and an active balancing BMS.
Well, Hyundai and Kia actually kind of democratized this with their eGMP platform.
Yeah.
That's what underpins the Ioniq 5 and the EV6. By utilizing 800 volts, they can deliver the exact same power with half the current.
Right, and half the current means significantly less heat generation.
Exactly. Less heat and thinner, lighter wiring. That is exactly how they achieve those crazy 18-minute charge times from 10 to 80%.
And then on the extreme end of the spectrum, you have Lucid Motors. Their 900-volt Wonderbox inverter is so miniaturized it literally fits inside a carry-on suitcase. Yet it's efficient enough to help deliver over 800 kilometers of range.
It really is a marvel of engineering.
But wait, what about Tesla? Because they usually lead on powertrain efficiency.
That is true. And Tesla actually pioneered silicon carbide in their vehicles way back in 2018. But for their high-volume passenger cars, they intentionally stick to 400-volt architectures just to keep manufacturing costs down.
Oh, I see.
Yeah, so currently, the Cybertruck is actually the only vehicle in their lineup that possesses that complete high-voltage, high-tech trinity,
Interesting.
which, leaves us with an interesting thread to pull on. If the onboard AI in these advanced BMS units can mathematically predict battery chemistry degradation hours before it physically happens,
Yeah.
how long until the car's brain starts actively managing your charging curve based on your personal daily driving habits, like optimizing the battery's lifespan before you even touch the steering wheel?
Wow. Now that is a level of automation I think we're all waiting for. Well, thank you to everyone listening for tuning in and mastering such a complex technical deep dive with us today. Until next time, keep questioning what's going on under the hood.